The next speaker would be Sohail Ahmed. He'll be talking about numerical modeling of hybrid 3D woven composites for stiffness and strength prediction. As we all know, these composites are very popular now, hybrid composites, material of the day. So we will be listening to an interesting talk about it. Welcome.
Thank you very much. Thank you very much. Hello, everybody. I'm Sohail Ahmed from Northwestern Polytechnical University, China. Today, I will be speaking about the 3D hybrid woven composite, which is basically the new form of composites. I will move to the sequence of my presentation. First, a brief background, then our objectives, then how we build the geometry, FE model, and then to the discussion on the results, and after that, and then we conclude and way forward. At first, a little background. The major failure mechanism in the composite laminated structure, which has been proved is the delamination behavior of that. And to control that delamination behavior, there are different methods which are being used in the past, is like stitching, Z-penning, and 3D weaving, which will be the main emphasis in this presentation. Although there are advantages when we use these kind of composites into different structures, but there are some challenges, like during the manufacturing. There are some voids and resin-rich pockets. Mechanical properties can be degraded, and the last is the predicting the mechanical properties. To predict the mechanical properties, the following methods have been adopted, like experimental, which is the most expensive one, analytical, which is lot of assumptions have to be adopted, and the numerical, if we do it properly, which can be the most accurate way to measure that. Now, there is another evolution of this 3D woven the 3D woven composite, that if we include certain different materials and we make it hybrid. So far it has been done by some authors experimentally and numerically. So we will see that. But now I will explain that what were the main objectives of study in this research. We basically focuses on investigating the effect of hybridization of 3D woven composite. At first, we have considered a baseline 3D woven composite, which is basically of the same material. And then in the second part, we have included the different material yarns to make it hybrid, and then the combination of two types of fibers has been investigated through the finite element simulation, and so that basically three type of configuration have been studied. At first, the whole carbon. In the second, the three Kevlar layers have been included, and all the others remain of carbon. And the third one is all Kevlar, to see the effect of all Kevlar, all carbon, and the hybrid one. At first, I will explain a little bit about the geometry. Geometry of the 3D plays a dominant role in determining their mechanical properties and strength properties. The WAP and the weft fibers run in plane throughout the panel with little or no undulation. Set of Z fibers run in the direction of WAP and are drawn from bottom to top. A detailed study has been presented by Karahan et al. In 2010, where internal geometry of the fibers in a 3D woven structure is characterized. In this, if we say if we see the WAP yarn is almost rectangular in the shape, and is being plotted. And for the weft yarn, in the middle is almost rectangular, but for the top and bottom, because during the weaving process is stretching of the Z yarn. It has some material loss. So by analyzing this this geometry, we have built complete one unit cell. One unit cell, and the dimensions, as you can see, is all other dimensions: length, width, height, and the dimension for each fiber is presented here. Its constituent properties for carbon and Kevlar is estimated through Sham's model, which is a very famous model for the composite laminates, and its elastic moduli, Poisson ratio, and its strength parameters have been calculated and used in the FE model. Now coming to the FE model, basically the partition feature-based modeling methodology is used. We have partitioned each section, and their interfaces have common, like matrix and like matrix with WAP yarns, weft yarn, and Z yarn. So there is no cohesive zone defined between that, and special care has been taken while we mesh the model, that the opposite faces of a unit cell, the nodes has been created, coincident nodes have been created to apply the periodic boundary condition perfectly. Now I will come to the periodic boundary conditions. Exploiting the periodicity of the woven 3D architecture. The periodic boundary conditions were specified in 4 vertical faces of the unit cell, which is this one. We have left the top and the bottom faces because the complete thickness in a unit cell, complete thickness has been incorporated. Certain sets have been defined. Front, faces, edges, and corners, and through this constraint equation, we have applied the constraints on the faces, the opposite faces and opposite edges and opposite corners. We'll go after defining the periodic boundary condition, displacement boundary condition have been defined. If we are examining the elastic moduli in direction 1, so the displacement and degree of freedom, it has an assigned value through this equation as well, and all the other values are unset, so it is free to move in all other direction, and similarly for direction 2 and direction 3. Now coming to the results, first the baseline carbon epoxy, which has been experimentally analyzed by Bogdanovich. In direction 1, the VAP direction, the main load carrying for fibers, as we can see, is a stress plot, and the main stress carrying fibers are the VAP fibers, and the result here are excellently matched with the experimental data. In the VAP direction, however, there is some difference in the elastic moduli and as well as the strength prediction, which is basically explains I will again show this figure. If we see closely the top and the bottom fiber's shape, here in the numerical model it is exactly rectangular, but here is we can see it is not exactly rectangular. So some more material is added. That is why in the numerical it is a little bit higher. The values are a little bit higher. If we built exact shape of the fiber, then it will come down. Now for the second and third configuration, for hybrid, in which we have used three fibers of Kevlar. And for all Kevlar, if we see that the knockdown of elastic modulus as well as its strength in the VAP direction and as well as in the VAP direction. Now I will conclude. The result for the elastic modulus and longitudinal VAP direction conforms excellently with the experiments within 4% of the error. For the strength in the VAP direction, the error was less than 8%. For the VAP direction, I have already explained in detail that if we built an exact geometry, then the result would be more close. Overall, the numerical model developed in this study provided relative accurate estimation of the tensile properties of non-hybrid and hybrid 3D woven composite. The approach presented here can be used to understand and quantify the effects of hybridization and fiber architecture on the tensile response of 3D woven composite. Based on the current numerical work of the specimen, some hybrid 3D woven composites are under manufacturing. We will do some experimental analysis, and we will show our results in the future. Thank you very much.
Thank you very much.